Unit 1, Chapter 3, Matter. It's going to be a kind of a shorter slides, but the importance is still in here, which might require a little bit of why I will maybe explain the things a little bit longer. Chemical properties are different than physical properties. Physical properties, if we remember from the previous one, do not change the composition. A chemical property causes change. Chemical causes change. So we have a causing a chemical change. So something is going to change in the composition of our substance, making something new. Chemical properties, we have to change it. If you remember again back into your 8th grade mineral and rock identification, you were doing a lot of physical property identification, but there was one test that if you took some diluted acid and put it on the compound or that mineral, it would bubble or fizz. And that meant it was a calcium carbonate because it bubbled and fizzed. That was a chemical property of those compounds, of that compound, calcium carbonate, that to give off the carbon dioxide gas, the water gas, as in theirs. And the only way to have done that was to physically change it. It is that solution was now then a calcium chloride in the end, and so it was not exactly the same. It was a new substance, and you can't change in that because it's changed. It's the only way to identify that is to see, does it react with acid. The only way you're to know if something will burn is to literally burn it. And so the flammability part of it, it will change it. If it's flammable, it will break it down. It will cause something new. Burn a piece of paper. It's no longer going to be that same thing. It's going to be reduced to the carbon that's the ash that's there, and the water and the carbon dioxide will be given off as reactants, and what's left is the carbon that made up a lot of times what that substance is. You take and make baking soda and vinegar. It's going to react. It's going to give you a sodium acetate salt. We'll do a lab with that later. And you're going to get carbon dioxide and water vapor given off. And so these are the only way you can identify those things is chemically reacting them. This is why I feel chemistry is important, is doing the labs. That's why this is still a lab-based class, is that you're going to go and do labs, and you're going to ask to identify things that are happening in the lab. Now, sometimes it will happen the way you want it to, sometimes it's not, but you want it to happen. Okay, that's why I kind of build a recipe with those chemical reactions that you are asked to do in the lab, and so that you can hopefully see what you're supposed to see at the macroscopic level to understand what's happening at the particulate level of matter. And so that's what we'll look at as we continue through. Now, chemical changes has to happen. These are the 4 ways to identify whether or not a chemical change has occurred. If one of these happens, chances are a chemical reaction happened, and so you have to be able to identify what was actually taking place. Permanent change in color. Now, this might be confused with taking a Sharpie permanent colored pen and marking it on paper. Well, that's paper's never done. Well, you can actually bleed out the compounds that are inside that Sharpie, and so that through a different mean. And so there are other ways to look at that. That's not a permanent color change. Burning a piece of paper is a permanent color change. Reacting zinc and hydrochloric acid, that hydrochloric acid is a clear colorless solution, meaning it's clear, you can see through it. Colorless, meaning it has no color. But when you react it, the zinc chloride solution has a kind of a grayish tone to it, and that's some of the zinc that's there. Gas or odor being formed. Gives off a smell. And ways to identify it. And so you're looking at it as gas or odor giving off. You take and react baking soda and vinegar. It bubbles and fizzes, and therefore you're going to have a gas being formed. You can take that same zinc and hydrochloric acid. It's going to create hydrogen gas, actually fairly violently. And with that, you're going to see light or heat being released. The vial in which that is happening is some reactions will give off heat, and they will be hot to the touch, where you actually have to be mindful of how hot they actually are. And some reactions will do the opposite, where they'll actually feel colder. And what that in that it's a different, and so you have a release, not releasing of energy, but a pulling of energy. And sometimes they might give off other means of identifying that a reaction is happening, but you kind of have a change in energy is maybe a better way of looking at it. So the first three are very easily seen, and you can light a candle. Ooh, look, it's lighting. Yes, the only reason the light won't be there if there's no smoke means fire. Well, that's because there's there's heat or light being given off. You don't allow oxygen to be there, the light goes out. Chemical change stops. The formation of a precipitate is one that we will look at more when we look at chemical reactions in Unit 6, but it is one that is a little bit tricky sometimes, is that the solid formed by mixing of solutions. Sometimes the solid looks like just like little flakes inside of a solution, and or sometimes it can be as well, it looks like thick gross mucus, and but it's kind of very difficult, and so to give you experience of seeing these types of things is why we do labs. You will be asked to look and identify all four of these. These four things are, we're going to look at them, or we will talk about them again, and so these four ways to identify are very, very, very important. I cannot stress the importance of being able to look at these four things and identifying them in the lab. And so that you can see, oh, look, a chemical reaction is happening. Even in our everyday lives, these things are happening. Changing of color. And again, the changing of color we do have to be careful on. But that's why we look at it and say, okay, is it changing because there's a chemical change? Or is it changing because, or is it still physically like that thing? And such like paper being with drawn on with a marker or something like that. Is it still just paper? It's just been dyed, and so it's not really a chemical change there. Even if you look at like a perm, as a girl gets or a guy gets their hair permed, there's an odor given off, and because you have an odor being given off, it changes things, and those people that go into that will identify, yes, you're changing the structure of the hair. And so there are some of those things that we have to look at, and so it's everywhere. It's everywhere. It's everywhere. But there's things that we have to look at, and so we'll look at these further. These are things that we're going to bring up over and over again, is these identification of, is a chemical reaction happening? How do you know? Which is the following is not a possible clue that a chemical change is taking place? Now, we'll look at this a little bit further on again in Unit 6, but it's starting of this so that it's not all new all at once, is that we're going to look at these chemical equations. And what is a chemical equation? Well, it's a shorthand way of telling you the story of what's happening. It's like your cliff notes for some big novel that you have to read for English class. You read the cliff notes so that you don't have to read the whole story. It kind of gives you like a brief synopsis of all the important parts. Well, in chemistry, that's really all we really wanted to talk about, and maybe that's why sometimes some chemistry people are not always the best at English, because just give me the important highlights and I'm good from there. And because in chemistry, and that's really what we're looking at, is in some cases the important parts. In some cases, in analytical chemistry, the important things are everything. Um, but we really want to know is the big ideas. I want I want to know, what are my reactants? What are my products? What do I need to know? What am I going to control? What's going to change? And so we look at what is the reactants. The reactants are on the left hand side, and the products are kind of what you're doing. And I always think about the chemical reaction as kind of a plant. You have the reactants, the raw products uh, coming into the plant. It goes through the plant. Well, plants produce something. And so it's through that as how it happens. So you have this red gobbledygook. Um, doesn't look like a whole much. It goes through the process, and you get kind of a blue squiggly line now. That's what was produced. A plus B produces C and D. That's what the products are. What is being there now? It does not always have to be. It can be gas, it can be odor, light, energy, heat, and those can be the parts of the reaction. It can be the A and it can be that D, or it could be either or. And so where some of this stuff happens is kind of important. But what we want to look at is the what is kind of what's going on, and being able to identify the reactants and our products are the important part. Which part? What's my reactant? What's the stuff that I'm starting with? The raw product. What's the raw thing? And the product. What am I producing? What is a reaction producing? What is it making? Which of the following is a chemical reaction? Now, kind of a little quick historical background and some of the roots and the basics of this. Antoine Lavoisier, which was in the late 1700s, was actually beheaded in the French Revolution, determined that matter was neither created nor destroyed during a chemical reaction. That matter stays where it is. Now, this was had to change around 1905, because we had to kind of adjust on how we said the law of conservation of mass. And now we have to say that in a non-nuclear reaction, matter is not created or destroyed. And so in chemical reactions, matter is not destroyed. If you burn a piece of paper, people like say, well, it's lighter, it's no longer the same. Well, you let the water and you let the carbon dioxide escape. And so if you were able to collect all of that, everything that you weigh out at the beginning, or mass out actually would be a better term, at the beginning of the chemical reaction, should be there at the end of the chemical reaction. And you have to be very meticulous, very careful about how you allow for that reaction to happen. You can't allow the gases to escape, because if you allow that to happen, you're not going to be able to capture them and measure them and see what is happening. So you have to be very careful and meticulous about that. So ultimately, the reactants should equal out. It's not like putting something together, putting a car back together and having a few extra washers and bolts and going, they left that in there on purpose. Those weren't needed. No, in a chemical reaction, if you have leftover stuff, chances are you did something wrong. Just like you should always kind of have everything that when you take apart something, you should always be able to put it right back together, and it should all fit. So that's kind of what you're looking at with that. The law of conservation of energy in a non-nuclear change, energy is neither created or destroyed. It can be changed from one to another. So we can talk about looking at the law of conservation of energy, that if energy is going into the system, a certain amount is going to come out of the system based on certain energies things. The energy tends to be a little bit trickier for us to really kind of pin our nose on, because we have to make really good measurements before and after, and there becomes this bond energies and some of the other things that we deal with in chemistry. So those bond energies are very difficult to measure, and that's why they're tabulated values usually. And so we look at that. Now we say that they can change from one another, and that's because in 1905, Albert Einstein wrote one of his many papers that year, in which the combined the law of conservation of energy and the law of conservation of mass. For many years, they were thought to be completely separate governing bodies of chemistry. And he said, no, not really. Actually, you can change from one to the other. And this leads us to the idea of nuclear energy. And so that's actually how we get nuclear energy to happen, is that we have these uranium enriched, in this country we would use an enriched uranium rod, and it gives off these little neutrons, and so you can give these little neutrons off here, and what that does is that hits a water molecule, and that energy is being, those neutrons from the uranium hit the water, and essentially starts moving because it has a lot of energy, and they're not just leaving very slowly; they're moving at a fairly high rate. And this then in turn this water molecule will hit another water molecule, and they'll keep bouncing and bouncing and bouncing, and it will boil the water, and that boiling water turns a turbine, and so that turbine, you get the little turbine here, starts spinning around, and that generates electricity. And what we always associate with nuclear power plants from the TV show The Simpsons is these big, huge cooling towers. Now, we have two nuclear power plants in Minnesota. They do not have cooling towers like The Simpsons do. Their cooling towers are much different. They have a different methodology. The amount of uranium they're using is much different as well. But the idea is that energy is equal to mass times the speed of light squared. Now the speed of light is about c equals speed of light, or Celerotros swiftness, and that's 300 million. A lot of zeros there. Love to have that in my bank account. Meters per second squared. The speed of sound is a relatively slow 330 meters per second. Now, if you paid attention to any track meets or anything such as that, we always say go by the flash or by the smoke, whatever comes first. Don't go by the sound. Well, that's because you will see the flash of the gun go off, well, about 1,000,000 times faster. That light will travel 1,000,000 times faster to your eye than the sound will. And this is very evident, say, in the 200. If you are standing at the finish line of a 200-meter race, which is one half a lap around the track, it is a noticeable delay. And so it's important. And so this is all happening. This change in mass is happening at this massive amount, and that's because you're squaring 300 million. And so there's a lot of energy that can be had from this. I believe it was Lisa Meitner who actually kind of tied the two together to allow for this nuclear energy to happen, although she was not given credit originally. Was her research partner, but that's something for a story for another time. During any chemical change, the mass of the products is So that kind of ends Unit 1. You should be getting ready for a lab around this time as well. Also, make sure that your notes are up to date, hopefully, and that you have everything written down and looked at, and look over these videos again, maybe for your convenience, so that you can prepare yourself for the test.